SwayamPrabha. Digital India. Educated India.
Hello and welcome. So in today what we'll get started with is the topic of flow visualization, where we've already seen quite a bit about imaging and some of the aspects involved there, and now we can start getting involved in the flow visualization, finally leading up to quantifying the flow fields. What I'd like to do now is I'd like to show you a video where you'll see flow in a microchannel. The relevant literature is right here. This is actually taken from one of my papers, which was published quite some time ago. But you have flow in a microchannel, and so you have flow that is going this way, and this is a microfluidic channel, and you have these walls right here, and your flow is going this way. The flow is seeded with particles. In fact, it is seeded with so many particles that it is difficult to make out the individual particles. So in the last lab session, you saw what happens when we put 1 micron particles into water, and this is what happens when you put a very large number of that kind of beads into the flow. So you can see the flow to some extent. It is difficult to make out the single particles, but you can see there is some amount of churning happening here. And this sort of a image actually allows you to do important quantification for understanding fluid flow. Now this is again a fluorescent imaging, so the background water is actually black. It's just because there are so many particles that what you see is basically a very, very strong white intensity across the entire image. And when just to explain what the actual flow in the system, what you had is this kind of a channel, and the flow was coming in from this side and exiting from this side, and you had these channel walls right here at an angle. And in this particular image, this is a numerical simulation of the actual fluid flow. These are in the red you can see the streamlines and the flow, and these streamlines also show that there should be these vortex structures that should be there in this small gap. And when you analyze the data through particle image velocimetry techniques, you get this kind of a vector field, which actually shows you that there exists a vortex, right? So you can see that there is this is the Eulerian vector field of the fluid flow, and you can see this type of a flow that is there. So you can use your experiments to validate any numerical simulations. Now the key here was the use of particles in water. We have seen this image before. This is from one of our lab sessions, thanks to Praveen and Abhinit's fantastic work in the lab. And I want to, before I get started with some of the important aspects of flow visualization, there is something I wanted to hit upon here. Now, in most imaging, to get good signal to noise ratio, for example in microscopy, the background liquid is often transparent, right? So if it is a gas, it's not going to interact very strongly with light. If it's something like water is transparent, it has no color, so it doesn't also interact very strongly with light. And in many of our imaging, the background just basically looks black because it's not interacting. But the problem is to visualize the flow field of the water or the gas, right? So something that is not interacting with light enough, you have to visualize and quantify the flow of that. So how do you do that? You cannot visualize flow easily in such a case. There are some techniques like Schillerin, which we will go into again, which allow us to look at flow patterns qualitatively in gases and use some of the weak interaction to visualize. But if you want very strong quantitative data, like in particle image velocimetry, we want the velocity field, it becomes very, very difficult. And that is where we have to use particles like this, and this becomes our tracer particles. Okay. So what we want is to seed the flow with tracers. Sorry, with tracer particles, which will help us illuminate the flow. Okay, that's the one of the backbones of particle techniques like particle image velocimetry. So that's what that's going to be one of the first things we want to learn when we start to learn particle image velocimetry, because it's going to be important to get good images where we can visualize flow. Okay, so with that I'm going to change to my notepad. Okay, so the problem at hand is flow visualization, and we are going to consider the use of tracer particles. But even before we do that, there is a couple of important aspects that need to be mentioned. Now, in theoretical fluid mechanics, there is an idea called the continuum approach. Which is used, and in the continuum approach, basically the idea is that the fluid is in a way an extension of the idea of space, and basically in any neighborhood of any given point there exists a collection of an uncountably infinite number of points. So it is a mathematical idea, but which allows tools of calculus to be applied to certain problems. Now, in practical considerations, when it comes to experiments, when it comes to visualizing flows and quantifying them, there is an important number which allows us to validate whether the continuum approach is correct or not. This number is called the Knudsen number. It's usually denoted by the letters Kn. So this is my Knudsen number. It is defined as the ratio of two length scales. And on the top you have the microscopic length scale, and I'll explain what that is in a second. And in the denominator you have the macroscopic length scale. Now, the microscopic length scale typically is the mean free path between molecules as they collide with each other, because that gives us an idea of how much free space is there in a fluid. Whereas the macroscopic length scale is the length scale that is associated with the flow. So if you have flow over, let's say, a ball, the diameter of the ball is the macroscopic length scale. Or if you have a flow inside a channel, length of the channel wall can serve as a macroscopic length scale. So this number should be much less than 1 if my continuum approach has to be valid. In fact, we say that for continuum approach to be valid, our Knudsen number should be less than 0.01, okay, for continuum flow. If Knudsen number is greater than 0.01, but still less than 0.1, then this is in the domain of what is often known as slip flow, where the continuum approach is more or less still valid, but you might encounter slip at the walls. So the no slip condition at the walls might actually be not exactly true. But as this number grows, so if this number is, let's say, between 0.1 and 3, then you end up into a zone called the transitional zone. And if Knudsen number is now greater than 3, then you have something called free molecular flows. In the free molecular flows, you have non-interacting molecular, very weakly interacting molecular impacts. Molecules usually don't interact with each other that much at all, and hence the name free molecular flows. Where would you encounter such flows? Well, I hope you remember the image of the nebula that I showed you in one of the classes. That would fall at a Knudsen number which has a very high number value to it, and hence the traditional techniques of tracers, etc., cannot be used. So when we talk about tracer particles, we will assume that our flow is such that this condition holds and our containment approach is valid. And this is quite important, right? Because the very fact that you are using a tracer particle means that you now actually have a proxy for the actual fluid particle. The fluid particle itself is not visible, and you want to visualize it through the use of a different particle. And obviously the idea is that the particles should follow the fluid flow properly, and we will come to that, how to figure that out, we will come to that also. But once you do that, just like we showed you here in this particular image, here you have in the red, what you have is are the fluid streamlines, which by the way are have to be computed. In a given experimental technique, what you usually will get is the Eulerian velocity field. From this Eulerian velocity field, you will have to create these streamlines. You can also create other visualization lines such as the streak line and the path line, and we will just quickly go over them as well. So, in flow visualization, these three lines are often referred to, the first being the streamline and the most possibly one of the most important ones, the second being a streak line, and the third being path lines. There are some other lines as well, but these are the most common, right. The streamline is very important because this line is such that the flow field is everywhere tangent to this line, right. So, a streamline is a line such that everywhere it is tangent, such that I will write such that ST, it is such that the velocity is always a tangent to it. You can show from this that the equation for a streamline is my dx by u, the x direction velocity, dy by uy and dz by uz. So, this is the equation which governs streamlines. I am not going to go into the derivation of it, hopefully you are aware of it. So, this is my equation of a streamline. So, if you have an experimental technique in which you are able to calculate ux, uy, uz, then you can use this particular equation now to calculate your streamlines in terms of x, y and z. Right. So, x, y and z, an equation connecting them, that would probably represent the streamline in this particular case. Then now comes the topic of streak lines. Now, streak lines are a line that connects all fluid particles that have passed through a certain point at some given time in the past. So, that connects all fluid particles that have passed through a certain point in space at some time, either in the past or the future. Okay. So, that is the key here. Now, it connects all fluid particles. I did not say some other massive particles. So, streak lines refers to fluid particles that have passed through a certain point. Now, how do you describe a streak line? Well, if it is a fluid particle, then you are following now the fluid particle as it moves along in passes through different points in your observation window, and you have to equate now the velocity, so at any given point that it passes through, the Lagrangian velocity will be the same as the the Lagrangian velocity of the fluid particle will be same as the Eulerian velocity that you measure. Right. So, the equation that describes them just says that you have to equate your Eulerian velocity field to the Lagrangian velocity of the fluid particle, where this equation, which represents an ordinary differential equation, has to be solved under a certain boundary condition, under a certain condition. So, where your x is at some t equal to t naught was a specified value called x naught, where x naught is now fixed and t naught is some variable, is a variable. So, by making t naught a variable, you allow for that particle to have passed through x naught at any given point, either in the past or in the future. Right? So, that is what a streak line is. And then we come to path lines. Now, path lines are probably the most intuitive of all of them, and the reason for that we will see, because path lines is basically a line just like the previous one. It is a line that connects fluid particles that have not moved through this any point at through a point at any time, but instead it is the movement of a given fluid particle as it passes through different points in space. Right. So, let us write down the definition for this. So, this is a line that connects a particular particle, a particular fluid particle as it moves from one point to another. Now, as I am referring to fluid particle and again is simply because if it is a massive particle, then you will actually have to solve for the equation of motion, the entire equation of motion, and you cannot just equate the velocity of a massive particle to the Eulerian velocity field at that location, because they need not be the same. But if it is a fluid particle of the same density, of everything the same, then they will be equal. So, the governing equation in this case is actually exactly the same. So, you again have the local Eulerian velocity is equal to the Lagrangian velocity of the fluid particle which you are interested in, and this now has to be solved such that your x is at some t equal to t naught, where t naught is now fixed, is equal to some x naught. So, you have to give the right initial condition, right. So, this is now fixed and this x naught has to be known for you to be able to solve. If you have a condition like this, let us say you had tracer particles in a flow, and if there was a flow imposed, in this case there was no flow imposed, but if a flow was imposed here and you took a long exposure photograph, then you would have, let us say the particles this particle moves like this, and you took a long exposure photograph of this, you will get this entire streak line, this entire line which is actually the path line. Right. So, the path line is probably the most intuitive of them to understand, but the other more important flow visualization quantification is in terms of the streamlines, because they are very important and relevant in fluid mechanics. So, what we want to do is now we want to be able to use tracer particles to understand flow in a given fluid, and we are going to look at how we can analyze some of the images of the type that I have introduced or I have shown you here. This is I will just show you again. There are tracer particles that have been seeded in the flow, and by analyzing the tracers I want to analyze or understand the fluid flow behavior. So, what I need are tracer particles, and the assumption is going to be that tracer particles should follow fluid streamlines or fluid particles as they move, okay, and not separate paths and not some of its own path. So intuitively, what are the things that can affect this? Okay, so intuitively, the parameters which can affect tracer behavior would be particle density, so my rho of the particle or the tracer, so I just put a p here, and my even the size of the particle, so particle diameter. The diameter should be as small as possible, right? So you have these different parameters which will actually impact how faithful a tracer particle is in following fluid flow. And intuitively you can say that there are different, some of these quantities like the particle density and the particle diameter will have an impact on the behavior of the tracer particle, or rather the goodness of the tracer particle. Now there is a way to quantify this further, and that is through a number called the Stokes number. Now the Stokes number is a number which is defined as, so Stokes number is defined as the ratio of particle response time to the fluid response time. So my Stokes number, I am going to define it as some tau p, which I will call the particle response time, versus some tau f, which is my flow response time. And I will see what each of these quantities are. Now my response time is basically a measure of how quickly a quantity responds to change, right. So if my so what happens when my Stokes numbers are of values that are greater than or less than unity. So let us say you have flow around some cylinder, and these are some of the streamlines associated with it. Okay. So on both sides here is the same. Actually, let me just copy this. That is going to make it easier. Okay, and okay. So I'll try to show what happens when you have Stokes number much less than 1, and what you have when you have Stokes number much greater than 1. So we'll try to understand this number intuitively before we actually come up with the equation for it. So let's say there are these particles in the flow. Now Stokes number much less than unity means that the particle response time is much smaller than the fluid response time. So the particle actually responds very fast. So as the flow changes, so the flow has some response time to this, but the particle changes its own direction faster than that. So in the Stokes number is much less than 1, the particle is able to follow these streamlines very nicely. Whereas if the Stokes number is much greater than 1, then as the flow changes, the particle is not able to change its location properly to align with the fluid flow, and you will have a situation like this where it can just go and hit the cylinder. So it doesn't, it separates out from the flow, and this is not appropriate anymore for good flow visualization experiments. So your tracer particle has to be chosen carefully, and as the Stokes number is much greater than 1, particle is unable to follow streamlines. So now let's see how you can quantify this number. I mean, we have just quantified it as a ratio of 2 time scales, one being the particle time scale and the other being the flow time scale. Now in a fluid flow, what does happen? So if you have a particle, right, let's say the particle started at a initial condition of when it was at rest with respect to the fluid, and then it has to accelerate and achieve the fluid flow velocity, right. So how does the particle do that? So we have to write the equation of motion for such a particle. So we have to basically write F equal to ma. For a particle, your of the density, let's say rho p, my total mass is rho p pi by 6 dp cube. This is your mass, and I have to now multiply it with the du dt, which is my acceleration, right. Okay, so this is my ma part. On this side now I have to write the force. So what is providing the force for making my particle move along with the fluid flow? It is the fluid drag. It's the fluid drag which entrains the particles and makes it move along with the fluid flow, right. So on this side we have the fluid drag, which I can now write as half CD, CD being the drag coefficient. My density of the fluid, which I'll write as rho f. So you have 2 rows here. They are separated, they are differentiated with respect to the subscript. So rho subscript f is the density of fluid, rho subscript p is the density of the particle. UF minus UP square, where U subscript f is the velocity of the fluid, U subscript p is the velocity of the particle, and this by the exposed area, which for let's say a sphere is pi d square by 4, right. Okay. So I hopefully all the quantities here are well understood, and just to repeat one more time, dp is the particle diameter, rho p is the particle density, rho f is the fluid density, and similarly for the fluid quantities here. So now to simplify this, this is an equation that we have to solve, but to simplify the right hand side, we are going to introduce a quantity called the Reynolds number with respect to the particle diameter. I am writing small d, so let me be consistent and just use small d here. So my here you have the relative velocity dp by mu f, where this is the viscosity of the fluid. I have assumed that the flow velocity is greater than the particle, because I am going to assume that the particle started out with a initial velocity of rest with respect to the fluid, and then has to accelerate to the local velocity of the fluid. Now this equation, this now can be simplified, and I urge you to simplify it yourself and check with me. On this side I am just going to retain my dup term, which is my time derivative of the particle velocity, and here I am going to write my other terms, which will now include my drag coefficient, my Reynolds number. And once you do this simplification, I am going to just simply write the completed expression right here, and I urge you to do this and make sure that my equation is correct. Okay. Now what is the value of CD? Well, for slow flows, we can assume that my drag coefficient for a sphere is my Reynolds number by 24. I am sorry, is the reverse, it's a 24 by Reynolds number. If you introduce this value of CD into the above equation. Now you can see why we introduced RE, right? RED. So it cancels, and you end up with a more simplified expression of my UP, which comes out to be 18 times mu F. Okay, there is a mu here missing. Sorry. 18 times viscosity, rho particle size, dp particle diameter square, UF velocity of the fluid minus velocity of the particle. Okay. So this now becomes an ordinary differential equation that can be solved. So solve this, solve using initial condition UP at t equal to 0 is equal to 0. And if you solve this, what you end up with, the solution of this comes in the form of my particle velocity is my fluid velocity times 1 minus e to the power minus t by a time scale, which is my particle time scale. So you can see this is the tau p that we are after, and this tau p now, where this tau p is rho by 18 to mu f. So now I have an algebraic expression for my particle response time, which, if you recall, is how we had started off with the definition of the Stokes number, where the particle response time was in the numerator. And now we have to figure out what the fluid response time scale is. Now the fluid response time scale is actually rather straightforward. So the fluid response time scale, or tau f, is nothing but my length scale of the flow divided by the flow velocities scale. Right? So if you combine these two, this gives me a Stokes number as rho p dp, and please correct me if I am wrong. I am just going to already derived this before. So this is a very, very important number, and you have to make sure that you, before you start using a tracer particle, you calculate this particular number for the tracer particle, and you will need information about the flow, right. So you can see that in the Stokes number, the approximate idea of the flow is already built in. That brings us to the question as to how do you know the velocity scale beforehand. You have to know what type of fluid velocity that you will get even before you actually do the experiment. That you can get by various physical considerations, let us say by imposing mass continuity. This is not, by the way, the local this is just a velocity scale in the system. So you have to estimate approximately what is the velocity scale of the fluid flow, and then you use that number here. The geometry of the system already defines or determines L, which is the flow length scale, and then you have to experiment with different type of particles to figure out what particle to use. Rho p will come from that. So if you are using, let's say, polystyrene that from a certain manufacturer, they will already specify the density for that. So you will have this information beforehand. Usually for particles you can choose different diameters. So this is something that is totally in your control. Finally, this viscosity term is well already predetermined by the fluid that you are going to do. So it is predetermined by the experiment. So this is a number that you have to calculate, and you have to appropriately choose a tracer particle so that the Stokes number is much less than 1, so that the flow field is accurately followed by the particle. So in this particular video that I showed you, that calculation had already been done, and these were these are polystyrene particles in water, which are actually behave very well when, especially polystyrene is a very nice tracer particle when it comes to water. It's usually neutrally buoyant and follows the flow fields very well. Okay, so I hope we learned an important lesson about choosing the right tracer particles, and we will follow up with other aspects of flow visualization in the next class. So with that, thank you very much.